So this is probably evidence of, in a sense, the first images of, the very first generation of stars. Hydrogen is not likely to be a fuel of the future. Gravity is probably not a force. AI is likely to cause severe problems for humans in the next 5 years. Okay, you get the picture. Now look, we cannot speak unambiguously. Language is always necessarily imprecise, to some degree. But science reporting by scientists and science communicators, it seems, is saturated in prophecies. Prophecies and hedges. Now sometimes this is okay. When people are uncertain, they should say that they are. But when we have a good explanation, there's no need to hedge if we're being rational. We can just say something is the case. And by is the case, I mean know to be the case. We can say gravity is not a force, which means I know that gravity is not a force. And what that does not mean is that I am certain without any possibility of being wrong that gravity is a force. It might very well turn out that one day the successor theory to general relativity reveals that there is some sort of physical pull on the fabric of space-time mediated by some kind of particle of the kind that mediates other forces, in which case it might turn out to be a force. But that is not the situation that we are in. We can say gravity is not a force in the same way that we can say kangaroos are not finches, and finches are not fish, or electrons are fundamental, or the sky is blue. We're fallible. We could always turn out to be wrong. But egregious forms of science reporting and news are often of the clickbait kind, where prophecies are made. I want to try and avoid that. So here I'm going to try and do some science news without the misleading epistemological baggage. We're not going to say what's probably the case. In other words, science news from a critically empiricist and rational perspective. We concentrate on realism, what is actually going on in the world, and not what is probably going on. We look at what possibly will happen, not what is likely to happen. We reflect on what the evidence has ruled out and how best to explain the evidence that does exist, not what the weight of evidence probably indicates to be true. Here we'll focus on explanations and experiments, not predictions and prophecies. Here we'll tell you what has been understood and what is yet to be understood, not coloured by subjective emotions, focused on our fears about the future, just comprehension and good old-fashioned learning about theories that explain the world. Admit our ignorance, avoid being prophets, and say how it is, and not what we hope, or in our expert opinion, prophesy what will come to pass. Let's leave that to Galadriel's mirror.
For the mirror shows many things, some things that have not yet come to pass.
I almost wanted to call this How to Report Science News. News. News being new is new. So it's not the olds. So there's uncertainty in what is new. Well, there's uncertainty in what is old as well, but especially in what is new. Look, journalists have a hard time agreeing on what just happened, what is happening on camera right now, or what happened yesterday. Historians have difficulty agreeing on what happened decades and centuries ago. Is it any wonder science communicators and scientists are uncertain about what was reported in the literature yesterday or last year? Okay, so how do we do this? What we should avoid is probably discovered. Here, take a note from the journalists. It's alleged that. They allege, they say, in times of uncertainty, just say you do not know. But it's alleged that, or they might have claimed something or other. They being the scientists. But always be willing to say, you don't know, I don't know. And rather often, that's what I'm going to say here. I just don't know. Without further ado, where did all of this come from? It is a sign of rapid progress that now almost everyone watching will be able to give some account in terms of the Big Bang and then stellar evolution resulting at some point in a supernova blast which scatters heavy elements: carbon, nitrogen, oxygen, aluminium, silicon, phosphorus, sulfur, magnesium, iron, indeed everything on the periodic table up to and including uranium and possibly beyond, namely all of those building blocks from which simple and complex compounds that occur naturally, from methane all the way up to DNA, can be produced. And ultimately, people and all of our technological artifacts. But how complete is that picture of the origins of our chemical world? To a Papyrian, there can be no complete picture, but the details will be filled in to a greater or lesser degree, and when one question is answered, 10 more, or even many more than that, rise up in its place. So the universe began with a Big Bang, and that explains the cosmic microwave background we see in every direction we point our telescopes, the heat remaining in the universe left over from the Big Bang. Okay, then the question arises, why is that background radiation so very uniform, indicating the early universe was very uniform, while the present day universe is anything but uniform? It's lumpy and filled with galaxies over here and there, while in other places the majority of the universe is completely empty space. Empty space, populated by lumpy galaxies, is not uniform. If we began in a Big Bang, why did it happen then and not later or earlier? Why did it occur with that precise force or pressure or energy expanding space? Why not faster or slower? For each answer we glimpse new questions, problems we can now see because a solution has lifted us just a little higher, bringing into view more of the unknown and more of our ignorance. So many will know that our story begins with the Big Bang, and it ends on this day, the day that you're watching this, with the present-day solar system. Well, hopefully it doesn't end, but you take my meaning. Time up until this point is explained by recourse to a Big Bang 13.7 or 8 billion years ago. A solar system that formed from gas and other material that existed prior to the existence of the sun, and that material is what the Earth is made from. All the elements on the periodic table that occur naturally on Earth. Here we have it all when it comes to the building blocks of chemistry. So these elements on Earth were forged elsewhere a long time ago, but not so long back as the Big Bang. Because we know that at the Big Bang, the hottest instant of time that has ever been, the very instant that space-time itself came into being, the temperature was so high, no solid matter could have existed. Forget solid matter, which would have melted instantly. Forget liquid matter, which would have vaporized. Forget molecules or atoms of gas, which would have shaken themselves apart. No material thing could have been. Temperature, among other things, is a measure of the average kinetic energy of, or speed at which, particles move, and in particular vibrate. As the temperature increases, particles shake more and more, and in the solid phase they can shake so much that they shake free of their bonds and begin to slide around one another. That's called melting. When liquid, they can shake so much they achieve escape velocity from the solid state and become gases. That's called vaporization. Shake a gaseous atom enough, and its electrons fly free from their nuclei, and shake even the subatomic particles enough, and they will shake themselves apart as well, being converted into so-called elementary particles, the quarks and leptons like electrons, and the bosons like photons. But those elementary particles are far from being atoms. Forming atoms, like atoms of hydrogen, requires necessarily a lower temperature. So continue to raise the temperature and everything will shake itself apart into its elementary particle constituents, so far as we know. So if you want to make an atom, you have to have a minimum viable temperature at which the atom will form. Otherwise the temperature will be too high and the thing will just shake itself apart. The forces that bond the atom together won't be sufficient to hold it together. So forming atoms, like atoms of hydrogen, requires a low temperature relative to that which existed at the Big Bang. But happily, if you're deciding to generate a universe using the Big Bang mechanism, there exists a simple law of physics that says if the amount of energy in a volume of space is constant, but then that space expands, as happened after the Big Bang, then the temperature will fall as that fixed amount of energy that you've got in your newly created universe must fill a greater region of space. And indeed, that's what happened. Space expanded after the Big Bang and has been expanding ever since, and the temperature fell immediately after the Big Bang due to that expansion. And the quarks, for one thing, were no longer vibrating quite so violently, so they could bond with one another. Take two up quarks and one down quark, and very well the gluons that bind them together as well, and one can form a proton. And thus, the very first chemical formed, hydrogen. In particular, positively charged ions of hydrogen. Or if instead we take one up quark and two down quarks, then we're able to construct a neutron. Once you've hydrogen atoms and neutrons and enough of them in your newly formed universe, then so long as the temperature remains high enough, those particles can bond together to form something called deuterium, heavy hydrogen, and tritium, even heavier hydrogen. Hydrogen with one proton, that's by definition, and two neutrons, that's tritium. But most interestingly, we can, if the temperature remains high enough for long enough, get some hydrogen nuclei to bond together and form a whole new chemical, helium. The process is simple if you know a little nuclear physics, and perhaps a little more complex if you do not. But this is a momentous series of reactions beginning with elementary particles, quarks, and stepping through various isotopes of hydrogen, resulting in helium. But here is our problem. We need a high temperature in order for fusion to take place. To have a proton and neutron bond to form heavy hydrogen presents a simple engineering problem. We just need to get them close enough together because they want to stick as if each particle is coated in a kind of superglue. That's the strong nuclear force. But if we wish to take hydrogen, to be specific, isotopes of hydrogen nuclei, the technical term for which is nuclide, nuclei with equal numbers of protons but different numbers of neutrons, if we want to get those close together, we have a problem because they're all positively charged, and positively charged nuclei repel one another. Like charges do that. But if our temperature is high enough, then our particles are zipping about fast enough that they can overcome that static repulsion and touch and stick and remain stuck. So there we have it. We can form helium. So why can we not keep doing this at the Big Bang? Well, by the time we have lots of helium in the early universe, formed by this very process, the universe has continued to expand at an astonishing rate. And as we've already said, an expanding universe means a lower temperature. Those particles begin to move slower, so now we have a triple-barreled engineering problem. On the one hand, the particles we wish to collide to fuse and form heavier elements, the helium we have just produced, are now moving so slowly they will tend to repel one another before they even have a chance to collide. And worse, helium is twice the charge of hydrogen, so it will repel any other positive charge coming towards it with twice the force as any hydrogen nuclei. Slower moving particles with twice the repulsive charge will not fuse together. And last of all, by the time we might have enough helium in the universe to produce other elements on the periodic table by this process of fusion, the universe has expanded so much that the density of particles is that much lower. So the chance of nuclei finding each other in empty space so that that fusion reaction can take place at all is so much smaller. The Big Bang, so-called Big Bang nucleosynthesis, is therefore over and done. And the universe now finds itself consisting of mainly hydrogen, 75%, and helium, 25% by mass, and many, many, many more photons, and much, 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 much more empty space. From this material, the first stars formed, then they died, and some exploded, spreading their innards throughout the space in between stars, mixing that material with pre-existing hydrogen and helium, enriching, as we say, the interstellar medium. And from this, yet other stars formed. Then some of those exploded and other stars again formed, and so it went, and the sun was eventually formed from what we say as some of that enriched interstellar material. And it's also what the Earth formed from, enriched by those supernova explosions. So that's it then. Case closed on how the solar system formed. That's the story since the beginning of the Big Bang. There is one step in this sequence I want to focus on now, and the title of this video no doubt gives some clue about this. There are many open questions in stellar evolution and how it is precisely the elements of the periodic table were formed. We could pull on many strands, but for me, one of the most fascinating remains the nature of those very first stars that were formed. By a quirk of history, the sun was labelled alongside many other stars that had telltale signatures indicating a high proportion of heavy elements in their atmospheres, population 1. Population 1 stars are said to be metal-rich, and that just means they contain a higher proportion of elements from lithium on up through the periodic table. Population 2 stars, on the other hand, have a far lower proportion of metals in general. But if one learns this as a student of astrophysics, one is immediately struck by the omission of stars with absolutely zero evidence of metals in their spectra. That is, after all, how we tell what elements are in stars at all. We point telescopes at stars, sure, but we can also attach to our telescope something called a spectroscope. And if you want to be really precise, you use something called an Eschell grating, which is a piece of glass with grooves in it. But there are all sorts of spectroscopes. The James Webb Space Telescope has a particularly advanced one. But whatever you're using, basically the idea is the same as what Newton did all those centuries ago. If Newton is famous for one thing after his explanations of gravity and motion, it was his investigations into light and passing white light through a prism to see it split into all the colours of the rainbow. Yeah, sure, others knew about this. Rainbows, after all, were a thing in the sky that anyone could see. But Newton did precise measurements. Whatever the case, the splitting up of light into spectra reveals what the light consists of, and without going into a lengthy exposition on the chemistry and physics here, different chemicals when heated produce different coloured light, different wavelengths. And so when we look at stars, we do not find a continuous spectra. In other words, we do not find all the colours of the rainbow, but something rather different and somewhat more complex. Sometimes missing dark bands from the continuous spectrum. Those are areas where so-called absorption spectra, absorption lines, where wavelengths of light have been absorbed by cooler gases. And emission lines, bright lines, caused by hot gases glowing. This is what anyone can see with a spectroscope in the chemistry lab by simply heating a gas in an evacuated tube at low pressure. We've all seen neon lights. Look at a neon light with a spectroscope if you can get your hand on a spectroscope. They're actually rather inexpensive. In fact, you can do exactly the same thing with fluorescent lights if you've got some of those. Each chemical, indeed, each atom and each complex molecule has a characteristic spectrum to first approximation. Chemists and astronomers in particular use such spectra to identify the chemical constituents of the thing they are observing. So this is how we know when we look at distant stars, for all the stars we can see, whether they're high in metals or low in metals, whether they're population 1 like the Sun, which are high in metals, or low in metals, which is population 2. But even the population 2 stars have some metals. They're merely low in metals. It's not like they have zero. So this implies the existence of a third population, population 3 stars. Stars without metals at all. Stars made solely of the Big Bang stuff, purely of 75% hydrogen and 25% helium, approximately. Why do these population 3 stars typically not feature in our taxonomy of stars? Well, they do, but they get short shrift if you're studying astrophysics and astronomy. Consult most texts in these fields, and these stars barely appear at all. This is peculiar for astronomy texts where in general, they linger over the unknown and the problematic. That's par for the course. There are open questions on dark matter and dark energy, and they have often whole chapters devoted to the mystery of these entities. Population 3 stars, however, the first stars in the cosmos, make it a hand-waving sentence that they are hypothetical stars. Hypothetical? Necessary would be closer to the mark. It is necessarily the case that the first stars to form formed from nothing but hydrogen and helium. What is mysterious about them is the fact they have not yet been observed. But really, is that mysterious? Well, because it's very hard to see things that happened just after the Big Bang. But the fact is, no telescope, it seems, hitherto, has ever captured light from a population 3 star that we know of. But as I say, is that really so mysterious? When I asked about this many years ago as a student myself in lectures, I was offered the idea that they would have been so massive that they would have been really short-lived, and therefore all of them have long since exploded as supernova. So of course now, 13 billion years later, we're not going to see any of them. Certainly not in our vicinity. But I thought, surely looking deep into space means looking far back into time. Well, why can't we see them there? Surely those photons are out there. But it was kind of implied that, seeing individual stars billions of light years away? A fool's errand. We struggle to see entire galaxies that far away. Well, that seems that then. And yet, as I say, those photons are out there. If those stars existed, then they would have shone brightly. And if we can observe the cosmic microwave background, then we can observe population 3 stars, surely. Population 3 stars occupy a curious position in astronomy and science generally. They're rather like the first form of life in biology, paleontology, and geology. It necessarily exists. They necessarily exist. But there has so far been no evidence found of them. The light from those stars is out there, ripe for collection. But our instruments have so far proved too feeble to collect that light. After all, they would be too small, and that light too dim compared to the whole galaxies. And they are so very distant, which is the worst combination in astronomy. Dim compared to whole galaxies, and extremely distant. But okay, the James Webb Space Telescope is designed to see dim and distant things. And more importantly, and here's the key, there exists a phenomena in the universe that allows for especially distant objects to be seen. Gravitational lensing. And just as it sounds, this is the physical effect whereby some galaxy, but typically a large cluster of galaxies, is between us, the observer, and some very distant object, like a very, very distant galaxy. The light from that very, very distant galaxy bends around the cluster in between us and the object, and as lensing does, magnifies the image. So we have this fortuitous arrangement of objects in the universe in certain circumstances, allowing us to see objects which might otherwise be physically impossible to observe given our present state of telescope technology. And if we take some of the astrophysical literature on this at face value, this effect can be striking indeed. One star is claimed to have produced light a mere 900 million years after the Big Bang at a redshift of 6.2. That's phenomenal. But this paper claims it to be true, and it's published in Nature and so on. In this particular case, they are waiting for the James Webb Space Telescope to confirm, as they say, with its spectroscope. We would say, rule out the fact that it's not a population 3 star rather than confirm that it is. That aside, perhaps they can image the spectra of this single star. Now, of course, over 900 million years, much can happen. In other words, between the Big Bang and when the star apparently existed, there could have been other supernovae going on enriching the interstellar medium there. In other words, this could be a second-generation star. We just do not know without the spectra. When we have it, we'll know. But right now, we don't know. And isn't it easy just to say that? We don't know. We don't know whether this star is a population 3 star. It's a candidate. Here's what we know. We've got this spectra from a star that could possibly be a population 3 star, but it did exist 900 million years after the Big Bang, so after all, it could be a second-generation star, but at the moment we don't know. Here's what it will take to know. We need spectroscopic analysis. I don't have to say it's likely a population 3 star, or that it's probably not a population 3 star, or anything of the sort. My hopes and dreams and fears don't have to come into it at all. This isn't that hard reporting on new science, is it, after all? Now, before I return to the actual point of this video, which is claims that some scientists have actually observed a population 3 star with the James Webb Space Telescope recently, I want to linger on some of the unusual possible properties of population 3 stars. Low metallicity can actually do something to the brightness of a star. In particular, what metals do inside of their stars is can act as a kind of reaction catalyst, which changes the rate at which fuel is consumed, among other things. Now, for other convoluted reasons, and among other factors, this can affect what's known as the Eddington limit, or the Eddington luminosity. Now, what that is this is the brightness you can calculate, or rather the maximum possible brightness that a star can have given a particular mass. Why should there be a maximum possible brightness that a star can have given a particular mass? Why should there be a maximum mass for that matter? Well, because if you have a certain mass, that means you have a certain amount of gravity. The strength of the gravity is determined by the amount of mass that you have. The gravity keeps the material held together, and the force that acts against that gravitational collapse, well, this is called the radiation pressure that comes from the core of the star, which is heating up under pressure. The hotter a star, which is determined by the temperature of the core, which is determined by the strength of the gravity on that core compressing everything together, the hotter the star, the more the material in it wants to expand. Hot things tend to want to expand. The heat is racing out of the star as radiation, and that radiation pushes on the atoms and the nuclei, trying to rip the star apart. But gravity keeps the whole thing held together into a sphere. So this is a battle going on between gravity in and the radiation pressure outwards. Okay, so there's a limit to how high the temperature can be and how great the luminosity can be given the strength of gravity, which is determined by the mass of the object. All very well. But some objects seem to exceed the Eddington limit. Or rather, maybe they do, maybe they don't. Eta Carinae, this unstable star, it might actually be 2 stars, it might be a binary star, we don't know, it seems to exceed the Eddington limit. But, of course, it's unstable, so maybe the rules don't apply to that because of the fact it's unstable. So Eddington's formula doesn't actually apply to it. But this Eddington limit concept leads straight to the notion that, well, there should be an upper mass for stars, period. After all, on the one hand, keep throwing mass at a star and the core is pressed more and more tightly together by gravity, and eventually you overcome the electrostatic force of repulsion between the quarks. The whole thing will collapse into a black hole. But, well, if the temperature is high enough at the core, well then the nuclei there, the protons, are moving about so fast that they won't be forced inside one another and vanish into a black hole. So again, we have a balancing act. But if we add yet more mass, we get more compression and we get a higher temperature. You compress a gas and its temperature increases. That's simple physics. Well, if that happens, then the rest of the star also heats up due to the energy coming from that increasingly hot core. So the core is hot due to the nuclear reactions going on there. And the hotter it is, the more that the core heats up the parts of the star where the nuclear reactions are not going on, namely the rest of the atmosphere of the star. And well, you can just imagine that if the core is so very hot because the star is so very massive, that the temperature becomes so great that the star expands so much that its outer atmosphere just blows away because it has expanded so far away from the core. Or, and this seems to be what most of these simulations and calculations suggest, there is an upper limit for the mass of the star, because with super high mass stars, well, the super high mass means super high compression at the core, which means super high temperature at the core, which means a rate of reaction that is so high that it results in an explosion. As you increase the mass of the core of a star, the temperature goes up, and the temperature causes an increased reaction rate. Nuclear fusion is happening faster and faster and faster. Well, there's an upper limit to that before the whole thing just is run away into a complete explosion of the core. The star literally explodes if it gets too massive, because it gets too hot, because the reactions are occurring at a rate that's too fast. And that's why you don't see stars with masses, above 100 solar masses. In fact, rarely do you see stars with masses above like 20 times the mass of the sun. They're very, very rare. And the reason is that once you get really, really hot, you simply can't accrete material fast enough. And astronomers know this because they do simulations of what would happen. So they're working in the laboratory of computer simulation, so not a real laboratory. But this is what the simulations tell them, and this is why you don't observe those things out there, because the laws of physics tell us, what a computer simulation should be programmed to do, and the computer simulations don't reveal these supermassive stars. Instead, all the material that should be falling into the star to increase its mass gets blown away because the core is already heated up, and heating cores cause the heating of the interstellar medium, which blows away any of the gas that would otherwise accrete to the star. The radiation pressure exceeds the gravitational collapse. Accrete means collect material to it, or collect mass to it, or sweep up mass from its surroundings and cause that stuff to become part of the star. To summarize that, in other words, a star can only attract gas and other material, dust, mass in other words, if the gravitational collapse, the pull on the material, exceeds the tendency of the radiation pressure due to the high temperature to blow all that material away from its surroundings. And yet, this is important to note, the peer-reviewed literature in science articles on this suggest vast masses for some metal-deficient, and in particular, population 3 stars. And this is one of the exciting parts about astronomy, there's this great disagreement in the field. You have people quoting masses for some of these primitive stars, these population 3 stars, of hundreds, 200, 300, 1,000, 10,000. And in one case, one paper I saw, the respected astrophysicist quoting 100,000 times the mass of the sun. Some stars out there possibly having this kind of mass. Now, those last two numbers in particular, 10 to the power of 4 and 10 to the power of 5 solar masses, 10,000, 100,000 solar masses. Well, I did write to one astrophysicist who was an author on one of these papers, and I didn't hear anything back. Am I seeing things? I wanted to know if I was seeing things in this paper, but no, apparently I'm not. I read it more than once. Why should this be possible? Why should this be possible? Why can we exceed the Eddington limit by that amount? Why wouldn't the temperature of a 10,000 solar mass star be so high as to blow away all the surrounding gas, preventing it from ever getting to that kind of a mass? Well, look, there is one possible mechanism here, and it's called the porous atmosphere, which is what it sounds like. If you've got a low metal atmosphere, in fact a zero metal atmosphere, then as the radiation comes out from your core, it just shoots right on through the star's atmosphere because it intercepts very little along the way. Photons have a very small cross-sectional area, and so too does hydrogen and helium. And thus, the star's atmosphere can't expand very much. The radiation won't cause the expansion of those stars, and therefore won't reduce their mass or the tendency for those stars to collect more or accrete more material under gravity, because hydrogen and helium alone are so small. Like I say, their cross-sectional area is so small that if you're trying to shoot these nuclei with the bullets that are photons, you're just going to miss them. The photons just never interact with the hydrogen and the helium. Or rather, they very rarely interact with them. The star literally leaks its energy into space without the star itself heating up much, as it does when you've got metal-rich stars, or even just some proportion of metals in those stars. So there's one possible explanation for the fact that these population 3 stars might on average be very, very massive and have a mass function or a mass distribution that is very, very top-heavy as compared to the stars we see around the Milky Way and nearby. Another way of putting this is that perhaps these population 3 stars, these massive, massive stars, are made of gas that has very low opacity. It's transparent. Now, opacity, it turns out, is actually accounted for by the Eddington luminosity calculations, and the formula used to calculate it includes a term for opacity. But still, there appear to be stars that exceed this limit, are observed to exceed this limit. As always, astronomy has delivered problems with the observations made by improved technology. The problems are the mysteries that drive the curiosity of astronomers and push people to create more creative theories and better technologies to see further and in finer detail, which is why we have the James Webb Space Telescope up there in the first place, and why we have better rockets, and why we have improved computers and lenses and spectroscopes and cameras and robots and code, and so it goes. We can read papers such as this one, titled Characterization of Population 3 Stars with Stellar Atmospheres and Evolutionary Modelling and Predictions of Their Observability with the James Webb Space Telescope. And well, as this is a video about population 3 stars, and here's a lovely paper about population 3 stars, let's read a little. What they say is, quote, a renewed interest in direct detection of individual population 3 stars has developed in anticipation of observations with the next generation of ground and space-based facilities, in particular, the recently launched James Webb Space Telescope. Using the main sequence properties of population 3 stars from the evolutionary calculations, in a paper in 2002, and new metal-free models calculated with the Tulsi code, some astronomers, one named Rydberg, estimated the observable properties of isolated primordial stars at a range of redshifts and stellar masses. Without gravitational lensing, population 3 stars appear too faint to be detected even at the lowest redshift, Z equals 2. And in extremely long exposures, 100 hours, Rydberg 2013 also considered the case of a favourable lensed observation through a given galaxy cluster, one of the largest gravitational lenses known. Even in the lensed case, a realistic detection was found to require either an extremely heavy population 3 candidate, greater than 300 solar masses, or a primordial star formation rate far in excess of theoretical expectation, end quote. So they're pouring a little bit of cold water over the idea that the James Webb Space Telescope is going to be able to show us evidence of these population 3 stars. But we shouldn't give up hope. I mean, as I mentioned earlier, there are these other papers, this one in particular, let's go to that, where, never mind 300 solar masses, this paper here titled, quote, The Evolution of Supermassive Population 3 Stars. And, well, let's just read the abstract. This was published in high-profile journal, the monthly notices of the Royal Astronomical Society, second only to the Astrophysical Journal, perhaps, for prestige in this particular field. And, well, here the abstract says, quote, supermassive primordial stars forming in atomically cooled halos at Z 15 to 20, and just by the way, that's an extremely long way off, are currently thought to be the progenitors of the earliest quasars in the universe. End quote. Just pausing there. So they're saying that these primordial stars, these population 3 stars, are thought to be the things that cause quasars. Okay, they are the reason for the existence of quasars that we can see. Curious, very interesting. Let's keep going. They say, in this picture, the star evolves under accretion rates of 0.1 to 1 solar mass per year until the general relativistic instability triggers its collapse to a black hole at masses of 10 to the power of 5. In other words, 10,000 times the mass of the sun. End quote. Well, that's another astonishing fact. I mean, they're quoting that possibly some of these stars accrete material at the rate of 1 entire sun per year. They're swallowing up an entire sun's worth of gas per year. That's massive. And they can reach a mass, this is a single star, reaching a mass of 10,000 solar masses, at which point the entire thing collapses into a black hole, and then you get your quasar. Well, yeah, this is a sort of a turn up for the books for me. I didn't think this sort of thing could happen. But, I'm not a professional astronomer. I'm an amateur in these areas. I might have done a degree in this, but I don't keep up with every single area of the literature. And so in reading this, I was sort of surprised at the numbers that they were throwing at me. But anyway, this is a good set of authors here. These people aren't cranks, so far as I know, respected universities and all that kind of thing. If I need a heuristic about whether or not these people are trying to pull the wool over my eyes, well, no, they seem to be, it seems to be astrophysics, as they will go on to say. They're using code, and the code is, of course, based upon known astrophysics, I presume. Let's keep going. What they write in the abstract. Quote, however, the ability of the accretion flow to sustain such high rates depends crucially on the photospheric properties of the accreting star, because its ionizing radiation could reduce or even halt accretion. Here we present new models of supermassive population 3 protostars accreting at rates of 0.001 to 10 solar masses per year, computed with the Geneva Stellar Evolution Code, including general relativistic corrections to the internal structure, end quote. Okay, so these people are not lunatics, but, they are using this code, okay, in other words, a simulation of stars evolving over time, programmed with general relativistic corrections. Okay, so in other words, corrections to the way in which gravity works to collapse a particular star, and then, of course, cause the reaction rate, the nuclear reaction fusion rate, to occur at a particular rate and have a temperature of a particular amount. And presumably they're looking at things like the Eddington limit to see whether or not this star would blow itself apart. I'm guessing. But to accrete material at that rate, swallowing up 10 suns worth of material per year, that is astounding kind of stuff. Okay, let's keep going. That seems like a quasar, but they're not talking about quasars. They're not talking about quasars here. They're talking about a star, the first stars in the universe, swallowing material at that rate to fuel their own brightness and fusion. Okay, so they're doing that. These stars are obviously not going to be stars for long, because you're getting up to 10,000 times the mass of the sun. Well, in terms of stellar lifetimes, my goodness. Okay, so they go on to say, quote, we use the polytropic stability criterion to estimate the mass at which the collapse occurs, which has been shown to give a lower limit of the actual mass at collapse in recent hydrodynamic simulations. We find that at accretion rates higher than 0.001 solar masses per year, the stars evolve as red, cool supergiants, with surface features below 10 to the power of 4, in other words, 10,000 Kelvin, towards masses of 10 to the power of 5, in other words, 100,000 solar masses, and become blue and hot with surface temperatures above 10 to the power of 5 Kelvin, 10,000 Kelvin, only for rates 0.001 solar masses per year. Compared to previous studies, our results extend the range of masses and accretion rates at which the ionizing feedback remains weak, reinforcing the case for direct collapse as the origin of the first quasars, end quote. Well, yes, that is certainly extending the range of masses and accretion rates. I mean, extending the range of mass up to 100,000 times the mass of the sun for a single star, accreting material at the rate of 10 solar masses per year. Astonishing stuff, if true. But apparently their simulation allows them to do this. In other words, the star is forming. The star is forming, and it's stable, and then the whole thing collapses into a black hole and forming a quasar. Okay, wow. So if we can, according to the simulations and the theory, have such high mass luminous stars, then perhaps James Webb, the Space Telescope, can indeed image these things, or at least get spectra of some. So has it? Well, let's go to this recent news, which is really the reason for this episode, because I am absolutely fascinated by this. The news, for what it is, comes down to a preprint, which is here, and it was picked up by a few different popularizers. Now, all research in astronomy is put into the preprint archive, as it's called. Anything ever that's published in astronomy always ends up here, delivered for free, but sometimes it doesn't get peer reviewed. But this is researchers using the James Webb Space Telescope. So automatically they have to apply to the James Webb Space Telescope Committee, NASA and others, to get time. So you already have to have a certain level of respectability in the field. So again, these aren't nutcases that are off the wall kind of thing. These are the real deal astronomers. Of course, that doesn't prevent them from making errors. They could, of course, make errors. But this particular paper hasn't yet been published in any of the astrophysical journals. They've submitted it to Nature. Okay, so possibly the most prestigious journal on the face of the planet. So they've bypassed the regular astronomy journals and they've gone straight to a general scientific journal, okay, which deals with all sorts of science. And so Nature wants to publish some of this stuff because, it's coming from the James Webb Space Telescope. The most fashionable thing in astronomy right now, the hottest thing in astronomy right now, is anything coming out of the James Webb Space Telescope. So, of course, Nature would want to publish it, and people want to publish in Nature, and so on. We exist in a culture of prestige, but happily for us, astronomy still has this culture of simply publishing stuff for free on the archive. And so quite often these papers, as they appear in the archive, appear almost identical to when they're published behind a paywall in Nature. Okay, but when you cite these things as a university student, or you need to reference them as an actual researcher yourself, you can't really do so until the thing has been published in the peer-reviewed literature. Well, you can, but you need to say it's not yet peer-reviewed. So everyone's waiting for this thing to be peer-reviewed. What does that mean? Well, it means a bunch of other astronomers, referees, are going to read this preprint and decide whether or not it deserves to appear in Nature. That's what's going on right now. And so it's been some months since this thing's been published, and we're still waiting for it to appear in Nature. So I don't know how they're checking this data and how they're checking exactly whether the paper is legit or not, but apparently that's what's going on. I don't know how many referees would read it too. Maybe they send it out to a dozen or something. Astronomers are forever complaining, by the way, about this kind of thing, because often the referees don't get paid. Sometimes they do, but quite often they don't. You're asked to be an anonymous referee. Read this paper and tell us your expert opinion on whether or not this is legit or not, or is there obvious errors here? And then once it's been through that process, then it gets published. That's what peer review is. So this paper that I'm reading from hasn't been through peer review. Although it kind of has, because, there are multiple authors here, and so they're checking each other. So that's one method of error correction. But also they had to apply in the first place to use the James Webb Space Telescope. So the very idea of what they were doing had to be presented to a committee of people who were experts, who had to tick off the fact that, yeah, this seems legit, this is working, and there would be technicians involved, and there would be a wider community of people that they're talking to, sharing their results with, before it even gets to the peer review stage. And then no doubt they've got colleagues that, are helping them out, and all that kind of stuff goes on as well. Once again, let's just read parts of this. In particular, let's just look at the abstract. It's titled, A Strong He2 Lambda 1640 Emitter with extremely blue UV spectral slope at Z equals 8.16, presence of population 3 stars, ? Okay, firstly, we need to unpack a little bit of that. What is this He2 stuff? So, as I explained earlier, every single chemical, every atom, every molecule has its own unique spectra. When you heat it up, it will glow. And if you look at this thing using a spectroscope, you'll see specific lines in the spectra. Okay, so helium has a particular spectra. Helium, if you continue to heat it, will shake around, it'll vibrate, we've been through that, and it will lose one of its electrons. That means it's singly ionized. It's lost one of its electrons. Now, helium holds onto its electrons very, very tightly. I'll come back to that. If you continue to heat the thing, then it will lose both of its electrons. You have to heat it really, really strongly, get it vibrating a real lot in order for it to completely lose its 2 electrons. But if you do that, then you've got this thing called He2, doubly ionized helium. And so it produces a spectral line of wavelength 1640 nanometers. There we go. Okay, so what does the abstract say? Let's read through this. Cosmic hydrogen reionization and cosmic production of first metals are major phase transitions in the universe occurring during the first billion years after the Big Bang. End quote. So this first part, cosmic hydrogen reionization. So what we have in the early universe just after the Big Bang is a temperature so high that hydrogen consists of one proton, and the atoms of it consist of one proton with one electron orbiting that proton. That's a hydrogen atom. So that would form after the Big Bang, once conditions have cooled sufficiently for the electron to bind itself to nuclei. Now, if you remove that electron, you get ionization. Now, you have so very early on in the universe, all of the hydrogen is ionized. It's just free protons floating around and free electrons. Because the temperature is so high, these two things can't bond together because everything's moving too fast. But once the universe is expanded sufficiently, then the temperature is cooled so that the electron can actually bond with the proton. I say bond with, but form a stable atom, a neutral atom. Well, when the first stars form, after this, the population 3 stars, they're very, very hot, and they can reionize things. So the free hydrogen that's floating around now, that is neutral hydrogen atoms, can be ionized again. They can lose their electrons. Why? Because the entire universe begins to heat up again. Why would it heat up again? Because it's got stars in it now. So initially it's really hot after the Big Bang. It cools down. The first stars form, and then the whole thing heats up again. And so therefore you get this reionization of certainly the regions around the stars anyway. Maybe not the entire universe, but parts of the universe become reionized. So that's what's being said there. And so they say this happens in the first billion years after the Big Bang. But this they go on to say, but still poorly explored observationally. Yeah, it's a bit hard to see things that far away that early on in the universe. Let's keep going. They go on to say, quote, using the James Webb Space Telescope near-spec prism spectroscopy, we report the discovery of a sub-L star galaxy at Z spec equals 8.1623 plus or minus 0.0007, dub something or other. Okay, so the James Webb Space Telescope near-spec prism spectroscopy, that's the instrument. Okay, and if you go back to my Origins video, also about the James Webb Space Telescope, I talk a little about this near-spec prism thing. And so this is the instrument that is used to do spectroscopy, to split the light up like Newton did, only in a more sophisticated way. So we can see these emission lines from these distant stars and everything else. We report the discovery of a sub-L star galaxy. Now, L star is the luminosity function which gives you the average galaxy luminosity at a given epoch in time. So right now, there are all these galaxies that exist in the universe right now around us, insofar as we can have a now. In other words, at Z equals 0, the 0 redshift. So the galaxies in the local group and further, galaxies in our neighborhood, there are bright galaxies and there are dim galaxies, okay? The average galaxy has a brightness of L star, and the Milky Way, by coincidence, is approximately L star. That's the luminosity of the average galaxy in our region. Now, if you go to Z equals 1, things are different. Z equals 2, Z equals 3, we're talking about redshift here. We're getting further and further away from the Milky Way galaxy. And the further away you get from the Milky Way galaxy, the further back in time you're going. So the conditions are different, the stars are different, the luminosity of galaxies is different. And so therefore the average luminosity of galaxies is different, higher. You go all the way back to near the beginning of the universe, and you've got these things called quasars, which are outshining everything in the known universe, right? And so therefore, near the beginning of the universe, the earlier you go, the much brighter things are. So what they are saying here is they're reporting on the discovery of a galaxy which is less bright than the typical galaxy at that redshift. So the redshift of 8.1, which is a huge redshift. That is just soon after the Big Bang. Okay, so it's a long way off. I don't know. You can be further than 13.5 billion light years away because the space can expand at faster than the speed of light. There are complications here. Let's not worry about that right now. Skipping a little of the detail here, they're saying that this thing, this galaxy, is a strong He2 emitter. It's got this emission line. This hydrogen 2 line indicates a high temperature thing. And in fact, they say it's the highest redshift He2 line currently known. Its high rest frame equivalent width is 19 plus or minus 3 angstroms. And they go on to talk about different lines, okay, different hydrogen lines here, Balmer lines, Balmer series. And this is all part of this particular galaxy's stellar populations, okay? So that the reason why they're seeing these lines in the galaxy's spectra is because, well, the galaxy's spectra is what the star's spectra would be. And so They then go on to say these could be population 3-like stars. Population 3-like stars. So they've imaged this galaxy, this sub-L star galaxy called RxJ 2129, and are saying that this is the most compelling case as we get towards the end of this abstract here, where trace population 3 stars might coexist with more metal-enriched stars. And of course, if you're a billion years after the Big Bang, something like that, then you've got this issue of, well, a lot can happen in that time between the Big Bang and a billion years. In other words, you can have generations of stars being born, exploding, spewing their contents throughout the interstellar medium, and then you're getting reformation of stars. And so you're having metal enrichment there. So if you've got population 3 stars mixed in with these population 2 stars, let's say, maybe even population 1 stars after all that time, the third generation of stars indeed, then you've got difficulties with, saying that, well, this light comes from population 3 stars because it's intermingled with all this other stuff. Okay, so that's the end of the abstract. So have they seen population 3 stars? Is the hype warranted from people who are talking about this as the first detection of population 3 stars? Well, as they go on to say, let's just pick it up in the paper. They go on to say, quote, "The nebula HE2 line requires a hard ionizing background radiation, which is usually attributed to Wolf-Rayet stars, stripped stars, X-ray binaries, or active galactic nuclei, AGN. The location of the galaxy, RxJ 2129, in the mass excitation diagram and the low limit of something else disfavour a supermassive black hole as the culprit." End quote. Okay, very well. But that's a problem, isn't it? If you're holding a gun, a smoking gun, and say, look, Jerry's fingerprints are on this, many might very well conclude, well, it's Jerry who fired the gun. Of course, if you whisper later on during the investigation, yes, technically Jerry's fingerprints are on the gun, but so are George's, Elaine's, and Kramer's, well, then you've still got the same mystery. Attributing the smoking of the gun to Jerry at that point is not a good explanation until you can refute that any of the others are in fact responsible for the shooting of that gun. So this does seem to be as if this is the line of reasoning for population 3 stars having been observed. Yes, population 3 stars are expected to have helium-2 lines in the spectra. Why? Well, because they're so hot. To remove the 2 electrons and doubly ionize helium, well, wow, that's some energy. That's some heat. Helium is the least reactive substance in the universe. Truly. To be reactive, you need to gain or lose electrons. But helium has 2 electrons and that's it. It wants to neither lose any of them nor gain any more. Its 2 protons in its nucleus don't want to attract any more. It's almost a perfectly stable atom, at least as stable as possible in this universe. It won't react. You can't burn it. You can't react it with acid. It laughs at oxidation. Nada, nothing. It's not going to react. That's helium. Those electrons are not going anywhere, and it is electron transfer that underpins all chemical reactions. All chemistry is about what the electrons are doing, where they are going, how they are being transferred between one atom or ion and another. It is the science of electron transfer. And for every other element on the periodic table, you can have some of this, even the other so-called noble gases. But you think about something like oxygen, it readily gains 2 more electrons, making it O2-. That's the ion. In the case of any metal, take lithium or sodium, they're more than willing to give up one of their electrons, leading to a positive ion. And so this is why certain metals are particularly reactive and why certain non-metals are particularly reactive, because they're very willing and able to give away or to gain electrons. Not helium. Not helium. Helium's electrons never get shared. They don't get transferred. In chemistry, you don't get molecules of helium-2 like you get O2. There's no He2. There's no He2O. There is no HEO. Helium does not make compounds because it doesn't react. And it does not react because it does not lose or gain electrons. It's holding tight onto those electrons. So that's chemistry. Okay, but physics says, We'll take those electrons off you if we can. All we need to do is to heat you up enough, increase your temperature, cause you, the helium atom, to move around so much, to vibrate so violently, to shake those electrons away. So shake it enough, raise the temperature high enough, and well, you'll get hell. He2. Hell is the shaking of helium so much at such a high temperature that you lose these two electrons. So yes, of course, this leads to the dad joke that's common in textbooks on this stuff. He2, doubly ionized helium, is hell. You need to be that hot. Now, another word for doubly ionized helium is alpha radiation. An alpha particle moves very fast, but they're much slower than beta radiation, which is electrons, and way slower still than gamma rays that move at the speed of light. But whatever the case, they've detected helium-2 here in this very distant galaxy, but they admit there are other sources that can produce emission lines of helium-2. So we're going to have to wait for the peer review, and we're going to have to wait for other papers, and in particular, people to write letters, astronomers to write letters that critique this idea. I'm not a professional astronomer. This is certainly not my particular area of astronomy, insofar as I do have an area of astronomy. And so we have to wait for the specialists in this area to talk about this particular stuff. But at the moment, I'm not saying that this is probably population 3 or probably not population 3. We're in the situation where we don't know. What we have is an interesting mystery. It could be the case that this is a population 3 candidate. But how they can separate out whether it could be some other source that's causing this helium-2, and whether or not you're actually seeing stars that are simply very, very hot, we don't know. Would aliens on planets orbiting these population 3 stars know that they're orbiting a population 3 star? No, because by definition, they couldn't possibly be there. Why could there not be aliens orbiting population 3 stars? Well, because remember what population 3 stars are? They're made of only Big Bang stuff, hydrogen and helium. Now, if you want to form a planet of any kind, if you want to form a planet on which aliens can actually arise, then you're going to need something more than hydrogen and helium. You want a surface for those aliens to exist on. Never mind that. You want to make the aliens out of something. And as we've just said, helium's not going to do it. Helium is the least reactive stuff in the entire universe. So could you make an alien out of hydrogen? Not really. Hydrogen can bond with itself, but unless there's oxygen around, well, you're not even going to get water. So you're not going to have planets around population 3 stars. You're not going to have aliens made out of population 3 material, because that is just Big Bang stuff. So that's my science news. It's exciting. We have to wait for this thing to be published in Nature. We have to wait for comments by other astrophysicists to find out whether or not we've seen the telltale signs of population 3. But it seems to me that it's not the smoking gun. We're not going to say, yep, there we go, population 3 has definitely been seen. It's just a big question mark. And so these authors are right to put the question mark there. If they can repeat this with the James Webb Space Telescope, looking at perhaps other galaxies, and they can refine their techniques, then perhaps this thing can be done. There are other papers out there that purport to use gravitational lensing to see individual population 3 stars. Whether or not you can believe that, I don't know. But this is interesting stuff. It's exciting stuff. The possibility of being able to do this at all, whether or not we have an answer here, or just an open question leading to yet more problems, allowing for the unending quests for knowledge, I don't know. But until next time, bye-bye.